Today, we will be talking about aggregation-induced emission, also known as AIE. Now you might be wondering, what is that? Or might have many questions, or as some say, can eat one ah? But don't worry, all will be answered soon. Let's take a journey back in time. Throughout the years, light has always been of crucial importance to humankind. For example, your torchlights, your lamps, and even the sun itself. These are some examples. In the world of science, the emission of light in the form of fluorescence occurs from luminophores. Basically, a luminophore is a functional group or atom present in a chemical compound, and it's responsible for its luminescent properties. Take for example, compound X. The molecule you see brightly lit is termed the luminophore, and is responsible for the compound's fluorescence. A simple analogy would be the firefly, in which the part of the insect that glows can be termed as the luminophore of the insect. Luminophores are commonly used in the field of biomedical research, either in solution or physiological environments. They are usually employed for simultaneous fluorescence imaging, electron and fluorescence microscopy, or even the visualization of tumor cells in rats and human beings. However, numerous studies have shown that the fluorescence and activatable effects of luminophores are considerably diminished with an increase in concentration. This is due to the tendency of these compounds to readily aggregate, causing a phenomenon known as aggregation-caused quenching, and it greatly reduces the effectiveness of these luminophores. This fluorescein molecule is highly susceptible to aggregation-caused quenching. When alone, it is highly fluorescent. However, when more than one of these molecules interact with one another, it leads to the effect of quenching. This decreases the overall effectiveness of the molecule as a whole. Fret not, scientists have come up with a strategy to combat aggregation-caused quenching termed aggregation-induced emission. But wait, before we move on to aggregation-induced emission, or AIE, we should first understand the structural differences between molecules that experience aggregation-caused quenching and AIE. Unlike large molecules such as fluorescein, molecules such as tetraphenylethene or TPE consist of these propeller-like structures which causes these molecules to fluoresce even when aggregating, but not alone. This fluorescence is due to the process of restriction of intramolecular motion. Therefore, when molecules like tetraphenylethene aggregate, it leads to an overall enhanced emission, giving the phenomenon of aggregation-induced emission. In the recent years, molecules that exhibit aggregation-induced emission, such as TPE, served as recognizable alternatives for the design of light-up probes in the biomedical department. This led to the development of novel and activatable probes based on AIE fluorescence for image-guided therapy and even the treatment of cancer. If we recall, the propeller-like structures of tetraphenylethene led to the process of restriction of intramolecular motion, leading to the process of AIE. Typically, TPE is conjugated to a bioprobe prior to usage in the biomedical sector. Now you might be wondering, what is the mechanism behind this fluorescence strategy? The first mechanism is termed site-specific reaction, and it involves a molecule or bioprobe conjugated to TPE. Then, a target molecule approaches a conjugate and cleaves the TPE from the original molecule. This process is repeated until multiple TPE molecules are cleaved and aggregate, leading to overall fluorescence. If that sounded too complicated, let's imagine a piece of steak with a bone in it. Then, a dog approaches the steak and eats everything, leaving only the bone. Imagine this process happening multiple times, giving many bones left, to which they fluoresce. Well, the bones don't fluoresce in real life, but you get the idea. The second and final mechanism is direct binding, and this is more straightforward than the first. A cell surface consists of many receptors, to which our molecule or bioprobe conjugated to TPE binds to. This binding leads to an overall fluorescence of TPE, and this strategy of direct binding is in fact more commonly used than site-specific reaction. We've come to the final part on learning about aggregation-induced emission, and this is where we talk about how it has played a key role in modern-day cancer treatment, such as photodynamic therapy. Imagine an organ that comprises of many cancer cells. Photodynamic therapy uses the direct binding of TP to these cancer cells. Once enough TP has accumulated onto these cancer cells, a light source is introduced at a specific wavelength which activates our TP molecules, causing a chain reaction which then activates our molecules to eventually lead to the death of these cancer cells. Photodynamic therapy, which employs the use of aggregation-induced emission, is indeed a technique that has proven to be effective within the recent years for treatment of cancer patients. We can conclude that the possibilities and applications of AIE in imaging and sensing are endless and probably only limited to the enterprise and endeavors of researchers. Who knows, maybe within the next 5, 10, or 15 years, we can expect AIE to bring about more state-of-the-art innovations, especially with its current capabilities and technological advancements. We have come to the end of our lesson on aggregation-induced emission. I truly hope you have learned something along the way. Thank you and see you again.